Hello, this is electrochemistry part 4. In this one, I'm going to try to introduce you to what's called a galvanic cell or a voltaic cell. I refer to them as either. And so, in these particular type of cells, what we're doing is we're taking a reaction like this one. Here we have a single replacement reaction where zinc takes the place of copper and produces copper nitrate, and then copper goes back into solid form. So what actually happens here and what's going on is that zinc is going to change in its electrons and copper is going to change in its electrons. So electron is going to move from one to the other. And so we talked about half reactions. So we can quickly just kind of assign oxidation numbers to this. If you see here, zinc in solid form is 0. On the other side, when it combines with 2 nitrates, sorry, these should both be 2, apologize about that. When it combines with 2 nitrates, then we see that it becomes a positive 2 charge. So what we have is an oxidation. What's happened is we've lost 2 electrons, right? So we got more positive. So here's our oxidation half reaction right here. Now we can also look at our reduction potentials and we can find zinc. Let's see. Here's zinc right here, and we see that this is the reduction. These are always in reduction form, but what we can do is just take that backwards and say that this is going to be positive 0.76, right, for the actual amount of voltage that will come from this. And then if we look at copper right here, so copper in this case is a positive 2, and on this side it becomes 0, so it's been reduced by 2. And so we can find copper on here, and if you go and you look at copper, copper is a positive 0.3 in that direction. So this matches up, it's reduction, so we have positive 0.34. So if you add positive 7.6 and positive 0.34, what we have is a total of 1.10 volts. And so what's happening here, and like we mentioned before, when you couple 2 half reactions where one has a negative reduction potential and the other one has a positive reduction potential, what's going to happen is that these are going to flow into each other. And all you need to do now is to make this transfer of electrons. You see, this transfer of electrons, we have electrons being transferred away from here, and we have electrons being transferred toward here. So this transfer of electrons, all you have to do is make sure that this moves through a wire, and if you do that, you can get an electrical current. So let me show you what that looks like. Here's what it looks like. This is a voltaic cell, and so what we see here in the voltaic cell is on either side we have a solid, on this side zinc, and we have a solid copper on this side, and there's a wire between them. Here's the switch, voltmeter showing our 110, which we already calculated over here. And so let me just kind of give you the parts of this. What you have in this solution then is you have a nitrate solution or a zinc nitrate solution, and you have a copper nitrate solution. And so what's going to happen is the zinc here is going to come off of the solid, and it's going to go into solution, right? Because that's what happens. The zinc becomes aqueous in this case. And so when that becomes aqueous, this over here, the copper in this solution, is actually going to go back into the solid copper, you see. So the copper that was aqueous is going to be solid copper. Now, for this to happen, they're separated. You see, they're in 2 different compartments. And so remember that we had to, for this to happen, we had to transfer electrons. The zinc had to lose 2 electrons and the copper had to gain them. So notice what's happening is you see the electrons moving where? Toward the copper. So the electrons actually have to move through then this wire toward the copper. And as long as this solid copper is gaining electrons, it's going to be pulling the copper in from the solution and adding to it. So essentially this is getting larger mass and this is getting less. Now what do we have going on here? This is what we call a salt bridge. So what happens as you lose positive ions in this solution, as your positive ions go into here, right? This is being neutralized because what's happening is we got our negatives coming in, our positives coming in here. But if we're losing positives, then this solution will just increasingly become negative. So because this solution increasingly becomes negative, we have to be able to transfer positive ions, and you see the positive sodium ions transferring in here. So it doesn't matter what ions you use, but the idea is that the cations have to be transferred to this is called the cathode end. So the cathode is your positive end, while the anode is your negative end. Your cations have to move to the cathode side because the positive parts of that solution are going on to the solid, and so it's becoming more and more negative. So you need to move positives in here in order to keep this neutral. If you don't keep this neutral, it's going to create a potential which will actually stop this from occurring, and you want the electrons to continue moving freely through here. So you got to have a salt bridge to essentially neutralize the solution, and cations go to cathode, so those kind of match. The anions go to anode, and those kind of match. And then the electrons, of course, always flow in the direction from the anode to the cathode. So they always flow in a direction of the negative to the positive, which is opposite from current. When we measure current, current is actually the flow of the positive flow. So this would be the negative flow. And so current, when we measure current, it's exactly opposite of this flow. So electrical current is exactly opposite. So that kind of gives you an overview, shows you how we calculate the voltage here using a reduction potential chart, and kind of giving you the basic setup. We're going to do a little bit more with this in later videos, but that kind of gives you a real quick idea about how a voltaic cell or a galvanic cell works.